Have you ever stopped to think about what's really happening inside your phone or your laptop? I mean, really think about it. It's like a crazy, bustling city in there, with microscopic parts working non-stop to keep everything running smoothly. And in that city, there are these unsung heroes, these little components that prevent total chaos. Today, we're going to pull back the curtain on one of the most important ones, one you've probably overlooked a million times: the humble capacitor.
But, before we can really appreciate the hero, we have to understand the villain it's always up against. And it turns out every single person designing electronics is fighting this invisible battle that can bring even the most powerful gadgets to their knees.
Come on, you've been there, right? Your computer just randomly reboots. Your phone screen freezes for no reason. A file just corrupts itself. It is so frustrating. And while your first thought might be, oh, it's a software bug, a lot of the time, the real bad guy is hiding in the hardware, in the very power that's supposed to be bringing your device to life.
Okay, so the heart of the problem is this thing called power integrity. The best way to think about it is like the quality of the food you're feeding your electronic components. See, modern chips are super dynamic. 1 nanosecond, they're just sipping a little power, and the next, they're chugging gigantic gulps of current. These sudden changes create a ton of electrical noise on the power lines, making the voltage dip and spike all over the place. That's what we call dirty power, and it's the real source of all those random, infuriating glitches.
So, how in the world do we clean up this electrical mess? Well, this is where our hero finally steps onto the scene. The simple capacitor is our first and honestly our best line of defense against all these power integrity nightmares.
Now, capacitors are pretty cool because they actually play two different but related roles. First, as a bypass capacitor, it's like a bouncer at a club. It sees all that high-frequency noise and gives it an easy exit route straight to ground so it doesn't get in and bother the sensitive circuits. Then, as a decoupling capacitor, it acts like a tiny personal water bottle for a chip. When that chip suddenly gets thirsty for current, the capacitor is right there to provide a quick gulp, preventing it from draining the main power supply and causing problems for everyone else. So one little component, two absolutely critical jobs.
And just like any good superhero team, you need specialists, right? You can't just have one hero for every single job. Not all capacitors are built the same, and depending on the situation, you need a different kind of hero. So, let's meet the team.
First up, we've got the aluminum electrolytic capacitor. This is your heavy lifter, the Hulk of the team. It has huge capacitance, so it's perfect for storing big pools of energy. Next, you've got the metallized film capacitor. Think of this one as the all-rounder, kind of like Captain America. It's got balanced performance, making it great for all sorts of circuits. And finally, my personal favorite, the multi-layer ceramic capacitor, or MLCC. This is the nimble sprinter, the Flash. It's super tiny, incredibly fast, and it's the perfect hero for zapping that high-frequency noise we were just talking about.
But hey, every hero has a weakness, a kryptonite. For those big electrolytic caps, they can literally dry out over time, especially when they get hot. Film capacitors, they hate humidity and can start to corrode. And those tiny brittle ceramic MLCCs, well, they can physically crack if the circuit board bends or gets too hot or cold too fast. Knowing what can take your heroes down is absolutely key to designing a system that's going to last.
And this brings us to what might be the single most important part of this whole story. You can pick the absolute perfect capacitor for the job, but if you put it in the wrong spot on the circuit board, it is completely, utterly useless. This is where the physics of the board itself comes into play, and it's fascinating. The secret villain in all of this is something called parasitic inductance. It's this invisible force that exists in every single wire, every copper trace, every little component leg on your board. And what it does is it fights against quick changes in current. And the faster the current tries to change, like with high-frequency noise, the more this inductance chokes it off. Think of it like a hose that gets narrower and narrower the faster you try to push water through it.
And this right here shows you what's really going on. A real capacitor isn't perfect. It has a tiny bit of resistance, sure, but more importantly, it has that sneaky parasitic inductance we just met. At a certain point, a high frequency, we call it self-resonant frequency, the good capacitor part and the bad inductor part basically cancel each other out. And at that point, it literally stops being a capacitor and starts acting like an inductor, the very thing that's causing the problem we're trying to solve.
So this is it. The whole game comes down to this one critical thing. We have to fight that parasitic inductance by minimizing the current loop. The path the electricity takes from the chip's power pin through the capacitor and back to the chip's ground pin has to be as short, as direct, and as wide as we can possibly make it. That's the golden rule. Just look at the difference. It's night and day. On the left, you see a long, skinny trace connecting the chip and the capacitor. That long path adds a ton of inductance, basically making that capacitor useless. But on the right, the capacitor is snuggled right up next to the chip pins, connected with short, wide traces. And notice the key detail. The connection to the ground plane happens after the capacitor pad. That creates the absolute shortest loop possible, and that tiny little change in placement makes all the difference in the world.
Okay, so we have our different types of capacitor heroes, and we know that placement is everything. So how do we put it all together to create the ultimate noise-fighting solution? Simple. We build a dream team. We combine the strengths of all our different heroes to do what no single one of them could do alone.
This chart right here is the money shot. This is what a beautiful, stable power supply looks like. On the side, you have impedance. That's the bad stuff. We want that to be low. And on the bottom, you have frequency. Each of those colored lines is one of our capacitor heroes. See how each one is only really effective in a narrow frequency range? But when you combine them, you get that beautiful black line at the bottom, a flat, low-impedance highway for power across a huge range of frequencies. That is a clean power network.
So here's the playbook. The big electrolytic cap acts like the main water reservoir, handling the slow, heavy demands for current. Then the mid-sized 0.1 microfarad ceramic, the workhorse of every circuit board, it takes care of all that mid-frequency noise. And finally, you put a tiny 10 nanofarad ceramic as physically close to the chip as you can to squash those super-fast, high-frequency spikes. When they all work together, they've got every possible threat covered.
Now, understanding all this isn't just some abstract theory. It's a practical superpower you can use to make your own projects way more stable and reliable. So let's just boil it all down to a simple checklist.
It's really just 3 simple rules. 1. Get that capacitor as physically close as you can to the pin it's trying to protect. Proximity is everything. 2. Connect it with traces that are short and fat. Why? To minimize that evil parasitic inductance. And 3, give it a nice clean direct path to your main power and ground layers using these little drilled holes called vias and place them right at the capacitor's connection point.
Seriously, if you remember nothing else from all this, just remember this quote. The entire game, the whole battle, is about making the path for that high-frequency current as short and as low inductance as you possibly can. That's it. That's the secret.
So the next time you look at a circuit board, don't just get mesmerized by the big, impressive chips. Look closer. Take a second to appreciate all those tiny little components sprinkled around them. Because in the world of modern electronics, it's very often the smallest, most humble part in the board that's doing the absolute heaviest and most important lifting of all.